So, so that mathematical conversation continues on today. What math professors do, right, when they research, is they add things to that conversation. And I think it's a terrible shame that our students don't get to at least see from a distance that this conversation is going on. So one of the things that I did with my calculus class towards the end of the year, I had a choice. We could either do integration by trigonometric substitution, which is interesting, to be sure. I like it. It's a neat little thing. Or we could do something else with that week. So what I did with my calculus students for the last week of class was I found a delightful 2-page paper written by a couple of professional mathematicians, Professors Kalkin and Wilf. I printed it off and I gave it to the students. And we read it together. It took us a whole week of class to read the 2 pages. It's written in an enormously dense and technical language. But it's something that the students could understand. You know, we had to puzzle through the definitions. The paper itself was arguing that the cardinality of the set of rational numbers was equal to the cardinality of the set of integers. I think it was actually the cardinality of the set of natural numbers. So that's the first sentence of the paper. You know, I had to sit down with the students and we had to talk through what on earth is cardinality, what are sets, what are rational numbers, and what are natural numbers. That took us the better part of a day of class to talk through just the definitions of those terms. And finally, what we arrived at was the paper was arguing that there are as many integers as there are fractions. That, you know, for every integer there's one and exactly one fraction. To about half the class that seemed normal. I don't think they'd really thought about it. To about the other half of the class that seemed very strange because between 1 and 2 you've got infinitely many fractions. So the paper was saying something surprising. The paper then went on to give 3 entirely separate proofs of that fact. So what we did as a class is we read their proof and we worked it through until we'd convinced ourselves they were correct. And again, that took days of class time as the students would bring up objections or bring up places where it wasn't clear to them how the mathematicians had gone from one claim to another claim. And we would have to dig into that and sort of show the intermediate steps and work it through together and say, okay, now we're persuaded that you can get from here to there.
You're engaging your students in a peer review.
Yeah. Yeah, that's what we're doing. We're doing a peer review of this paper. And the students are in some sense peer reviewing their own understanding of the paper too, to convince themselves that the mathematics that's been done is correct. You know, so what that exercise is doing is it's encouraging the students to become peers of real mathematicians. It's encouraging them to be able to listen in on that conversation and to be able to participate in that conversation. And I think that's powerful for them. You know, that shows them that there's something going on in math beyond just the cookbook, something appealing and something that they can participate in.